This is Lab 1, Constant Velocity. We'll begin with a brief introduction. The purpose of this lab is to observe the motion of the object that is moving at constant speed without changing directions and compare our observations to a computational model created via GlowScript. The models and fundamental physical principles used in this lab are as follows. Newton's first law of motion states that an object at rest remains at rest and an object in motion remains in motion at constant speed and in a straight line unless acted upon by an unbalanced force. Newton's second law of motion relates the net interaction between system and surroundings to the observed motion of the system. The position update formula states that the final position is equal to the initial position plus the average velocity times the change in time, and the velocity update formula states that the final velocity is equal to the initial velocity plus the net force divided by the mass times the change in time. And the reasoning for using these principles are as follows. Newton's first law defines constant velocity motion. Newton's second law explains why the net force is zero. And the position and velocity update formulas are used to update the position and velocity respectively for each time step so that the motion of the system can be predicted. For the preview of main results, it was found that the position versus time graphs of the ball from both GlowScript and Tracker had a linear slope, and it showed that the system being observed was in constant velocity. For the experiment, the system was the stress ball, and the surroundings were the force applied, gravity, and friction. For the initial conditions, the object was at rest, the observation start time was t equals 0.867 seconds, and the initial position of the stress ball was 0.07918 meters in the x direction. For this experiment, a video of a stress ball rolling across a coffee table was recorded and uploaded to Tracker. The position of the ball was recorded incrementally with respect to time, creating a position versus time graph depicting the observed motion. For the code, line 32 initialized the system mass, lines 35 and 36 initialized the velocity and position vectors of the ball, line 40 was the size of each time step, line 56 calculated the net force, lines 59 and 60 applied the momentum principle, and line 63 advanced the clock. This was the output of the code. The graph on the left shows the position versus time, and the graph on the right shows the velocity versus time, and both of these slopes are indicative of constant velocity. Both datasets represent a linear positive slope, meaning that the motion of the ball is in constant velocity, and this is indicative of Newton's first law. Dataset 1 is extracted from GlowScript and dataset 2 from Tracker. Possible sources of error include not positioning the Tracker tool at the exact center of the stress ball, errors in my code, namely the initial conditions, and not inputting data correctly into Excel. For the what-if question, I responded by saying that if I were to flip the axes, the slope of the graph, originally positive, would become negative, but the value of the slope, or the magnitude of the velocity, would remain the same. For the what does it mean question, I responded by saying that it is not possible to say how many pushes and pulls are added together exactly to give zero net force, as there were many external forces acting on the object, such as friction, gravity, and air resistance, that cannot be calculated by observation alone. However, since the net force is zero, we do know that some of the forces will cancel each other out. In conclusion, we were able to create a position versus time graph via GlowScript by using the momentum principle, and compared it to a position versus time graph created from a more manual analysis of motion via Tracker. Although the position versus time graphs extracted from GlowScript and Tracker were not identical, they both had a positive linear slope, indicating that the motion of the stress ball was in constant velocity. This experiment also helped showcase Newton's first law, namely that an object will maintain its velocity and momentum unless it undergoes an interaction.